Hello students, I am Harshal Warade, Assistant Professor from Sanjani College of Engineering, Kopargaon. Welcome to my new lecture on Unit 6, Introduction to Advanced Materials. Today's topic is composites, basic concepts of composites, various types or classification of composites. Let us start with introduction. What exactly is a composite? A composite material can be defined as a combination of two or more materials having significantly different physical or mechanical chemical properties that results in better properties than those of individual components. The constituents retain their identities in the composite, that is, they do not dissolve or otherwise merge completely into each other, although they act in concert. Composites are one of the most widely used materials because of their adaptability to different situations and the relative ease of combination with other materials to serve specific purposes and exhibit desirable properties. The main advantage of composite materials are their high strength and stiffness combined with low density when compared with bulk materials. Let us learn classification of composite materials. So in previous slide what we have seen what is meant by composite materials. In this slide we are going to see classification of composite materials. The composites or composite materials are classified as mainly two constituents are matrix and a reinforcement. So matrices or matrix, they may be different one, that is polymer, metal, ceramic, carbon and graphite. So in polymer there is type of thermosets and thermoplastics. In case of metal matrices there are alloys. In case of ceramic matrices there are glass, ceramics and cements as matrices, and last one is carbon and graphite. Organic or polymer matrix composite (PMCs). Two main kinds of polymers are thermosets and thermoplastics. So different thermoplastics are available there in market. Polyethylene, polystyrene, polyamides, nylons, polypropylene are thermoplastics, whereas different thermosets are also available there in markets, that is epoxies, phenolic polyamide resins, polyester. Thermosets have the qualities such as a well-bonded three-dimensional molecular structure after curing. They decompose instead of melting or hardening. Thermoplastics have one or two-dimensional molecular structure and they tend to at an elevated temperature. They tend to melt at elevated temperature and show exaggerated melting point. Another advantage is that the process of softening at elevated temperatures can reverse to regain its properties during cooling. Metal matrix composites, that is MMCs. Metal matrix composites are high strength, fracture toughness and stiffness are offered by the metal matrices than those offered by their polymer counterparts. They can withstand elevated temperatures in corrosive environment than the polymer composites. MMCs are widely used in engineering application where the operating temperature lies in between 250 degrees Celsius to 750 degrees Celsius. Matrix materials are steel, aluminum, titanium, copper, magnesium and superalloys. Ceramic matrix composite, that is CMCs. Ceramics can be described as solid materials which exhibit very strong ionic bonding in general and in few cases covalent bonding. High melting points, good corrosion resistance, stability at elevated temperatures and high compressive strength, these are the advantages of ceramic materials. CMCs are widely used in engineering applications where the operating temperature lies in between 800 degrees Celsius to 1650 degrees Celsius temperature. Carbon-carbon matrix composite or CCs composites. CCs are developed especially for parts that must operate in extreme temperature ranges. They are composed of a carbon matrix reinforced with carbon yarn fabric, 3D woven fabric, 3D braiding, etc. CC composites or carbon-carbon matrix composites meets application ranging from rockets to aerospace because of their ability to maintain and even increase their structural properties at extreme temperatures. The advantages are as follows: extremely high temperature resistance, that is 1930 degrees Celsius to 2760 degrees Celsius. Strength actually increases at higher temperatures. High strength and stiffness, good resistance to the thermal shocks. Okay, let us learn now functions of a matrix. The matrix in composite material has different functions to do. It holds the fibers together, it protects the fibers from environment, it distributes the load evenly between the fibers so that all the fibers are subjected to the same amount of strain. It enhances the transfer properties of a laminate. It improves the impact and fracture resistance of a component. It carries the interlamellar shear. What are the desirable properties of a matrix? The desirable properties of matrix are as follows. It should have reduced moisture absorption. It should have low shrinkage. It should have low coefficient of thermal expansion. It must have strength at elevated temperature depending upon application. It should have low temperature capability depending upon application, and it should have excellent chemical resistance depending upon the application. Now there is another type of classification of composite materials depending upon the reinforcements. Different reinforcements which are there, they are used here they are used as fillers here for composite materials such as fibers, viscous, laminars, flakes, field. So fiber reinforced composites. The fibers are the important class of reinforcement as they satisfy the desired condition and transfer strength to the matrix constituent, influencing and enhancing their properties as desired. So I have shown here two figures: random fiber reinforcement composites and other is continuous fiber reinforcement composites. Second type is laminar composites. Laminar composites are found in as many combinations as the number of materials. They can be described as materials comprising of layers of materials bonded together. These may be of several layers of two or more metal materials occurring alternately or in a determined order more than once and in as many number as required for specific purposes. Figure shows laminar composite and sandwich composite also. Next type is particulate reinforced composite. Microstructures of metal and ceramic composites which show particles of one phase shown in the other are known as particle reinforced composites. Square, triangular, round shapes of reinforcement are known, but the dimensions of all their sides are observed to be more or less equal. The size and the volume concentration of the disperse distinguishes it from dispersion hardened materials. Figure shows the particulate reinforced composite. Flake composites. Flakes are often used in place of fibers as it can be densely packed. Metal flakes that are in close contact with each other in polymer matrices can conduct the electricity or heat, while mica flakes and glass can resist both. Flakes are not expensive to produce and usually cost less than the fibers. Figure shows flake composite schematic diagram. Field composites. Fillers may be the main ingredient or an additional one in a composite. The filler particles may be irregular structures or have precise geometrical shapes like polyhedron, short fibers, or spheres. Fillers may be the main ingredient or an additional one in a composite. The filler particles may be irregular structure or have precise geometrical shapes like polyhedron, short fibers, or spheres. Microspheres. Microspheres are considered to be some of the most useful fillers. Their specific gravity, stable particle size, strength, and control density to modify products without compromising on profitability or physical properties are their most sought after assets. Solid microspheres have relatively low density and therefore influence the commercial value and low weight of finished product. Studies have indicated that their inherent strength is carried over to the finished molded part of which they form constituent. Hollow microspheres are essentially silicate based, made at controlled specific gravity. They are larger than solid glass spheres used in polymers and commercially supplied in a wider range of particle sizes. So, what are the different factors which affect the properties of composites? Let us see the different factors which affect the properties of composites. The type, distribution, size, shape, orientation, and the arrangement of the reinforcement will affect the properties of the composite material and its anisotropy. The figure itself shows the different parameters which are responsible for factors affecting the properties of composites. Thank you.